Use the Maclaurin series expansion for cos x to determine the series expansion of cos squared x over 3 in ascending powers of x up to and including x to the 4. Well, we can state the Maclaurin series for cos x. Don't need to prove that. We've got to get that cos squared x over 3. So we can actually truncate all of this and just go up to x to the 4 and cos x. Then x over 3 is going to be 1 minus x over 3 squared over 2 plus x over 3 to the 4 all over 24. That gives us, we're dividing by 9, then by 2, x squared over 18. And then, okay, you probably want your calculator for this one. You're going to be dividing by 81, and by 24 ends up being x to the 4 over 1944. So that means cos squared x over 3 is just this times by itself. And you can see why we could truncate, because if I had the x to the 6 terms, there's no way I'd be able to use them like to get terms in x to the 4. Probably worth writing out like this and making sure you're being careful. So we're going to get 1, and then we're going to do 1 times minus x squared over 18, but we're also going to do minus x squared over 18 times 1. So we're going to get 2 lots of it, and we're going to get minus x squared over 9, because it's 2x squared over 18. I've just then simplified it. Then I'm also going to need to go with 1 times x squared over 144, but also that one there. All right, this time I'm going to write it as 2x to the 4 over 1944, because there's one other way I can get my x to the 4 term. Sorry, I know there's lots of little lines going around, but it's going to be from here. So it's also going to be from plus x to the 4 over 18 squared. And that's it. If I've dealt with the ones, I've times 1 by all of them. And then the x squared over 18, I times by the x squared over 18. The x to the 4, there's no other kind of multiplying, because I'll get x to the 6 here, I'll get x to the 8 here. No good. So then just put it together, 1 minus x squared over 9, and then put this bit in your calculator, you actually get plus 1 over 243 x to the 4. And that is our Maclaurin series. Really nice way of getting it for things like cos squared. Right, next up, we're asked to use our answer to part A and calculus to find an approximation to 5 decimal places for this integral. So the thing we've just found is right here, and then we're dividing through by x. But the integral is going to become integral from pi over 6 to pi over 2. And then just take our expansion, divide every term through by x. I'm going to get 1 over x minus x over 9. Actually, let me write that as minus 1 over 9x. Then plus 1 over 243 x cubed. And let's integrate. I'm going to get ln x minus x squared goes to half x squared, so we're going to get 1 over 18 x squared. And then divide 1 over 243 by 4. That actually gives 1 over 972 x to the 4. Now you don't have to write, like sub it in. Often with these sorts of integrals, yeah, you would then write a whole line putting it pi over 2 in place of x and then minusing. I wouldn't worry about it here. Just put it in your calculator. But do it carefully, and this is how I advise you do it. Get pi over 2 in as an answer, and then just do, rather than having to write pi over 2 every time, we just do ln answer minus answer squared over 18. You can use the fraction button if you prefer. Plus answer to the 4 divided by 972. 0.32076. Now our final answer needs to be to 5 decimal places. Actually, there was an 8 after it. In fact, I might write down another one, 3. Okay, and then I'm minusing the same thing, but with pi over 6 put in. But this is why this method is really good, because now we can type in pi over 6, get it as our answer, press up, and it brings back the calculation. I just need to press equals to use my answer. And there we go. Amazing. So I'm minusing minus 0.66218. Okay, write down a few more figures. This then gives 0.982951 to 5 decimal places, 0.98295. It's approximate, remember. Now, the next part asks us to actually use the integration function in our calculator to evaluate the same integral, giving our answer to 5 decimal places. A little hint, by the way, when you're doing integration questions and you're not given the answer, is to do this anyway and compare it with your answer, because then you'll know that whether you're going to be accurate or not. Of course, we're making an approximation here, but we're still expecting to be in the same kind of ballpark for a good approximation. Let's give it a go. Integral, and make sure, yeah, I think we have to be in radians here. I'm not sure it will work otherwise. 1 over x, and then cos squared x over 3, right? So be careful here. Cos x over 3, bracket, close that bracket, and then square it. I think if you put the cos is the squared there, I don't think it works very well. And then pi over 6, and pi over 2. We get an answer that is very close, 0.982801. 0.982801. So I'm just going to round it straight away to 5 decimal places. And then assuming that the calculator answer in part C is accurate to 5 decimal places, comment on the accuracy of our approximation. So we can see that they agree up to here. They're going to agree to actually to 3 decimal places. They would round to 0.983 each of them. So that's all we got to say. So pretty good, given that we just went up to x to the 4.